Hello students, I am Professor Ambika Devi, Assistant Professor of Physics, Government First Grade College, Bidar. Today's video is related to session 29 of BSc 5th Sem Solid State Physics course, which is prescribed in the colleges affiliated to Karnataka State Wilbarga University, Kalburgi. So, let us now begin with the session 29 of BSc 5th Sem Solid State Physics course, and this session is related to Weiss theory of paramagnetism. Now, we will study what is paramagnetism. The materials which possess a little net dipole moment are called paramagnetic materials. In these atoms, what happens when the electrons are rotating? When the electrons are rotating, they make dipole moment. Normally what happens, a dipole moment in a one particular direction and dipole moment in another or in its opposite direction. Actually, the number of electrons are so large that they are equal to each other. Then the net dipole moment is 0. That particular materials will not shows any magnetism. But students, there are few materials in which the dipole moment in one particular direction, here dipole moment in one particular direction is stronger than the dipole moment in another direction. Then they possess very weak dipole moment. Okay, but they do have such materials are known as paramagnetic materials. So students, paramagnetism is a form of magnetism whereby some materials are weakly attracted by an externally applied magnetic field and form internal induced magnetic fields in the direction of the applied magnetic field. Okay. Now we will discuss Weiss theory of paramagnetism. As we already studied the Langevin classical theory of paramagnetism, but this Langevin theory fails to explain complicated type of dependence of susceptibility upon temperature. The Langevin theory also fails to explain the relation between paramagnetism and ferromagnetism. Then later in 1907, Weiss introduced the first modern theory of paramagnetism. So students, Weiss introduced the concept of internal molecular field in order to explain the complicated type of dependence of susceptibility. Students, in real gas, what happens? The molecules are mutually influenced by their magnetic movements, and consequently there should exist within the gas a molecular field. This field produced at any point by all neighboring molecules, and this field is proportional to intensity of magnetization, that is represented by M. Here the internal molecular field is represented by Hi, and this Hi is directly proportional to intensity of magnetization. Hi directly proportional to M. And this equation, this is given by Hi is equal to lambda M. Here lambda is molecular field coefficient. Then the external field H acts upon the field. Therefore, the net effective field should be given like this. HE is equal to H plus HI. Here H is the external field and HI be the internal molecular field. After substituting HI, after substituting HI, that HI from equation 1 in the above equation, then we get H is equal to H plus lambda m. Here H is the external applied field. Okay, then from the Langevin theory, following from the Langevin theory, along with this field, here M is given by intensity of magnetization is given by from the expression N m square mu naught He divided by 3 kT. Already we know that He is equal to H plus lambda m. This He value is substituted from the above equation. After substituting the He value, we get this expression. Here N is the number of dipoles per unit volume and m is the magnetic moment of each atomic dipole and k is the Boltzmann constant. Lastly, T be the absolute temperature. Okay, next is rearranging the terms. We get m into 1 minus nm square mu naught lambda divided by 3 kT, which is equal to nm square mu naught He divided by 3 kT, where we know that C is equal to nm square mu naught divided by 3 kT. After substituting C value in the above expression, here C value is this one. After substituting C value in the above expression, then this expression is simplified as m into 1 minus C lambda divided by T. This lambda remains as it is and T remains as it is. In place of nm square mu naught divided by 3k, we are substituting C. So this expression becomes m into 1 minus C lambda divided by T, which is equal to C He divided by T. He by T as it is. In place of nm square mu naught by 3k, we are substituting C value. After substituting theta is equal to C lambda, then we get m into 1 minus, in place of C lambda, we are substituting theta. So it is theta by T, which is equal to He divided by T. Then m is equal to what happens? He by T, and taking this bracket from this side to that side. So it becomes m is equal to this expression. So students, we know that susceptibility is defined as the ratio of intensity of magnetization to the intensity of magnetizing field, that is psi is equal to m by h. Psi is the ratio of intensity of magnetization m to the magnetizing field, that is h. Substituting substituting the value of m from the above equation, we get C by 1 minus theta by T into T. So after simplifying, we get C by T minus theta. Psi is equal to C divided by T minus theta. Here C is the Curie constant and theta is called paramagnetic Curie point or the Curie temperature. This equation is known as psi is equal to C by T minus theta. This equation is known as Curie-Weiss law. So, students, below Curie temperature, if T is less than theta, then what happens? Susceptibility becomes negative. That is, paramagnetic would become diamagnetic. However, for most of the paramagnetic substances, Curie temperature is quite low. So that a situation for which T minus theta is rare. I hope students, all of you got good understanding of the concept of Weiss theory of paramagnetism. I hope you have enjoyed this session. Thank you.